So it will also be about coloring. Last talk, but here it will be about edge coloring that most of you are familiar with, but it will be from a more algorithmic point of view, spend a little bit more time maybe defining this stuff that maybe that you're familiar with. And then we will see that a very simple approach like optimal, but then kind of different stuff like most for improving with simple optimals. So let's start with the beginning. So edge coloring. So you're given a graph, and our goal is to color the edges in as few colors as possible. And the constraint is that no two incident edges will see the same. Okay, so for example, here it's not okay to add blue, that means the same vertex. Change it, we get the coloring of the edges that is red, orange, green, and if we verify every vertex as one. That's a valid color. Coloring. I can tell if this is like a huge number of colors we can use for edge color in the graph. And see, yes, because the max degree is 4. Okay, we will prove out for the max degree by delta, and obviously the number of colors we. I mean, a combinatorics, I guess both of you know this, it's always a graph, but it's a huge difference between edge color almost to its trivial low one. Always a graph is very almost delta. All right, so if you look at algorithms, this in theorem actually gives a polynomial, so patient algorithm gets a polynomial. And actually, this here, as a particular point, you actually identify color, edge color graph. That's kind of nice that it will really fine, nearly time that is fine at delta 1. You ask why not delta? Well, actually, it's empty hard. We don't believe in the efficient algorithm to distinguish whether you follow delta or delta 1, but delta plus 1. Okay. In special cases, you can do delta color like 5 plus 1. This is being considered dependent. And as a title suggests, today we're going to look at online life. I don't know if you've seen this before, so let me spend some time on this. What's an online algorithm? Normally, edge color with no graph. In an online algorithm, the instance is revealed in stages, and you need to make irrevocable decisions. So the traditional motivation of this would be a run or buy situation. Your work happen should be done in you don't really know the work. So this example would be at the beginning of you start to buy. In a box, roughly the number of days you're going to ski that is unknown and you get into. That's a run. Right situation we can irrevocable decision without knowing. Another classic example is like if you circle the web, that's very good. Okay, so then you get a lot of response, but you also get ads. Okay? And these are generated by an online algorithm that displays ads without knowing that you really optimize this bad, this example. That's like a classical, I guess, monetary interest in. In our clean setting of edge coloring, the following becomes alpha. And it's important that they don't. Okay, so before the graph has gone offline, now it's moved online. Let's say I know the vertex set and I know the max degree, but I don't know the edge. Now I present you first step. Without knowing the future edges, you need to color it. I give you a second edge. You need to color it without knowing the future red. Orange. So you need to color the edges without knowing. You know the vertex edges, you know the max delta, you don't know the graph. is introduced to you in an online manner. You need to make a decision. You can consider like the graph could arrive with vertices and so on, but just for information, we are considering the most general model. Edges arrive one by one. The order is completely adversarial, so the strategy should work within a certain order, a vertical order, and we are not looking at that. The question is like, how many colors do you get? The degree is given. Yes. So this turns out to be otherwise problem. It's the shift. The most input I would think. Okay. How many colors do we need? Is it still delta, or does it the fact that we don't know the whole graph impact on that point? Is the question clear? So, I need proposal of strategies how we can follow edge color graph of mode. Like it turns out that the previous strategy is optimal. Any idea? Oh, yeah. All right. So that would be like, okay, wants to form a 3D arm. Okay, well, that's kind of think of the colors as natural color with the lowest color available. Introduce a new color. So this would be as follows. I gave an edge, 1 is available, give an edge, 1 is available, 2 is available, lowest color available, 3, here's 2. All right, so that's greedy. Now, how good is greedy? All right, it's not terrible. It's not too hard to prove this is the most true delta. Why? On an edge E arrive, at most delta minus 1 edges arrive to the left hand point, most delta minus 1 edges arrive to the right hand point. The total number close to the full time of 2 delta minus 2, if I have a palette of 2 delta minus 1 plus 1. That's good. The issue is what? Like the fact is this is fine. Okay, so there are graphs with reduced delta. Why? I give you a star with delta minus 1 color. Okay, you will color this using color 1, 2, 3, 4 up to delta minus. I give you a second star. Your greedy algorithm is deterministic, it just colors it 1, 2, 3, 4, 5, exactly in the same way as the first. I continue giving you star, I give you delta identical, like delta star with delta color with delta minus 1 level. And I finish it off by 1. Okay, so now all these stars with the first delta minus 1 color, to color these delta edges, you would need to use delta fresh color stated to delta. So greedy, easy. After 1 of 2 delta minus 1 and this delta 5. I'm going to ask, what about other algorithms? Okay, so the advantage with other algorithms, see here, we use that all the colors are, all the stars are colored like that. But imagine, hey, what about me doing a more interesting algorithm that is not so, even like I could do randomization? Okay, so a general line may not color stars equally, but what you can observe is that, if I give enough stars, and here enough is in bold, enough stars, we know, well, delta minus 1 has to be colored the same. So if I give you enough stars, clearly delta minus 1 has to be colored the same. All right. So you cannot put them to learn. And if you do the calculation, which was done by binomial 1 in 1992, it turns out that you cannot be greedy, but only for low degree graphs. Or specifically, if you do the calculation, you cannot do better than greedy if delta is little of log n for deterministic and delta little of root log n. So there's a difference. You know, in these strategy games, do I allow you to do randomization? Hello. Good. It's good to taste. So. Okay. All right. So, yeah. So there's a difference when you play this online game, right? Do I allow you to only use the permitted strategies for random weapons? Okay. So that's why the lower bound is weaker for random. You can imagine if you follow these stars deterministically, I can always identify delta -1 guys at the same time. If you do it randomly, only with a certain probability, how they follow that. That's why the low bound. Okay, so that's kind of boring. We already finished with the greedy, optimal graphs. Of course, we're interested in, is this the only low bound? Okay. The conjecture from 92 says basically the only abstraction as well. So there's a huge difference. If the greedy is smaller and log and we're deterministic, we will not do better than greedy. And then the conjecture is a pretty bold conjecture 92 is that if you have more than logarithmic degree, you basically do as well as we possibly as possible. So this is bold conjecture. Let me just emphasize with things in the flipping context. It is, they could have been even bolder if they wanted because they allow randomization and they only require the weakly log. Could have said deterministic logam or randomized. It doesn't really matter. The lower. Okay, so that's the conjecture. So this has been quite some work on it. So in special cases, the conjecture has been proved in the affirmative. So I said, like, we are given a graph step by step, the edges arrive in an adversarial order, meaning that the structure should work in any. Right. So graph is step. All right. Okay, great. Okay, so now. Okay, so now it's good. Okay, so for the general problem we're discussing, the first improvement actually on greedy was 3 years ago. It was by Kulkarni, Liu, Zhang, Shani, and Tanaski, and they got E over E minus 1 delta. This is less than 2, so it's a asymptotic improvement. All right, so why am I staying here? So the conjecture is, like, we are proving this conjecture. So that's a picture of my co-authors, Joachim, Radu, and David. And what is nice is that I think it's pretty easy technique. So you will see, I think, an overview, and if you understand, hopefully you understand today's talk, then you can fill in the details. So I think the whole proof is like 5 pages. Okay. And more that you should care is that, okay, then we sweat a little bit harder. So like a year later, we can actually kind of prove that even the lower bounds they prove were tight. Okay, so if you allow for deterministic, log n is the right threshold. If you allow for randomization, root log n is the right threshold. Okay, but I will talk about the simpler first result mainly, and then I will comment a little bit about these sharp thresholds. But it's as I said, you sweat for a year and you can push it. Okay. Okay, so the outline now of the remaining part of the talk is that I will talk, there's a connection between edge coloring and matchings. Okay. You can probably see it. Then we'll talk about how to do, we will develop the algorithm for this matching problem together. I think there's kind of only one reasonable algorithm. The difficulty is how to analyze this algorithm. So I will kind of discuss a little bit the difficulty of prior work and how we overcome this. All right, so what's the connection with matchings? All right, so I call the following, I call it a fair, or we call it a fair matching problem. All right, so we are given a graph as before. Now our goal is to output a random matching M online,
so that every edge is taken with probably at least 1 over alpha delta. For some alpha, at least 1. Okay, so we want every edge to be in the random matching with good probability. Okay. So I have a randomized algorithm. So here it's only about randomization. I'm given a graph online in our case. In the end of the day, I want to output a matching, which is random because I have a random algorithm, but I want it to be fair in the sense that every edge is included with a good probability. All right, I claim that this is very related to edge coloring. First, there's easy direction. If I have an alpha delta edge coloring algorithm, that implies an alpha fair matching algorithm. Do you see that? What, you're nodding, so why is this true? It is true, but do you know why? Or anyone sees this? So if there's an alpha delta edge coloring, if we can call it, let's say, forget about alpha, if we can delta edge color the graph, I can output a random matching so that every edge is in 1 over delta. Yes. Yes, output every color defines a matching. If I have an alpha delta edge coloring, just pick a random color, output that match. Okay. But requires a little bit more work. This is known, like, I think Khan used something similar for list coloring in his work page 96, but this is also known online. What requires a little bit more work that can be done is that if you have a matching algorithm, you can turn it into a coloring. Intuitively, what's going on here, I run my matching algorithm, I carve out an edge color class, I repeat. Okay? You have to be a little bit worried, but this is the intuitive. No, because you really like you will like half the degree and then you repeat. Yes. No logs. That's important, right? We all right. By the way, okay. Okay. So for now, let's just be happy with this. And now we know that our goal in life is to find an algorithm for finding a matching so that every edge is roughly taken with 0.1 over delta. Okay? Right? That's the fair matching problem. Okay, so more specifically, match each edge with probability, we say 1 over delta plus q with some small q. I claim that there's kind of one natural algorithm here. All right, so I get to see the first edge E1. Remember, I need to pick each edge in the matching with probability 1 over delta plus q. At least probability 1 over delta plus q. So with what probability should I pick E1? Well, yeah, with that probability. Because if I pick it with probability 1, it would be fine, but it's stupid, right? Because then I would obstruct future edges. I pick it with probability 1 over delta plus q. Great. There's two outcomes. With probability 1 over delta plus q, I picked E1. With probability 1, the complement probability, I didn't pick E1. All right, so now E2 comes. In this scenario here, when I picked E1, I cannot pick E2, right? It doesn't form a matching. In the other scenario, I could pick E2. With what probability should I pick E2? Conditional probabilities. We need to scale up with the probability that the endpoints are free. Fantastic. Okay, so that's the reason. Yes. No. So there's two results: deterministic, randomized. Here we do the simpler randomized. I will comment on the deterministic at the end. Okay. No. And okay, I will comment because it's an open question part of it. Okay. All right. So, but let's stay calm. We do randomized. Like for example, give me an easy deterministic algorithm that colors stars differently. Okay. You need to do that. So it's not so easy. All right. Anyway, so now we have randomized. We came all up with this algorithm. There's like one reasonable algorithm to do, right? And we continue. Okay. So that's the algorithm we agreed on, right? We need to scale up the probability that we take an edge, probability, like with the probability that we could take it. Okay, great. So by definition, we pick every edge with probability 1 over delta plus q. Like that's the definition. So what's the issue? Like, otherwise we will completely, like, how come we didn't solve this like 20 years ago? there is a minor issue here is that, the scaling factor might become too big, leading the PTs to not be like valid probabilities. Okay. So that's why you need a slack Q. If you don't have a slack, it's kind of easy to prove that the scaling probability becomes too big. All right, so now we can discuss when can we guarantee that the scaling factor is not too big. It turns out that it's easy to prove that things work well if the graph is a tree. Why is this easy to analyze? When at ET arrives, the probability that U is free is independent of the event that V is free. Remember, we wanted to, the scaling factor was the probability that U and V are free at the same time. If the graph is a tree, these two events are independent. So you can just look at, probability UV free is equal to the product, is at least something, and you do the calculation. This works if you have a slack of root delta. So if you use delta plus root delta colors, this would be working if the graph is a tree. The problem with general graphs is that things get difficult. The correlations can go in both directions. Like if I condition on U being free, it might decrease the probability that V being free. So the way prior work dealt with this was to controlling the correlation. So give me two high-level examples. All right, so let's look at first vertex arrivals, which is a special case that part of the vertices already arrived. The green vertices arrive, but now all the edges incident to the green edges arrive at the same time. So it's an easier setting because we only get to see one edge at a time. Here you get to see all the edges at once. Okay, and we need to select a matching incident to this guy. Then this guy comes, we need to select a matching. All right, so let's look at two versus U and V. I claim that the event that U is free and V free here, for kind of any reasonable argument, are negatively correlated. Okay, so if U is taken, if I condition on U not being free, that kind of increases intuitively the probability that we took this edge, decreasing the probability that we took that edge. So they're negatively correlated. If you have worked on this, on matchings in biotech graph, at least in algorithms, this is something that shows up all the time. They are very nice, they lead to like nice correlations and so on. Okay, so this allows one to use Chernoff bounds and so on, and this kind of the idea why vertex arrivals in biotech graphs are much easier than the general graphs. So the point of this slide, maybe you don't understand, but the point is general graphs, hairy correlations, biotech graphs, kind of known techniques allow you to bound the correlation, apply concentration. Now for general arrivals, we have this hairy correlation. So what these impressive people did was the following idea, which is a nice idea. So let's say sample graph G down to a sparse graph. All right. In particular, what they do is to subsample the graph so that it locally looks like a tree. Okay, they want the, up to, let's say, I think it's log n over log n height or something, you don't encounter any cycles. Okay, so subsample the graph so that it looks like a tree. We don't know the correlation on the leaves of the tree, so let's not worry about what happens in the tree. But we're interested in what happens between the endpoints, whether U is free and V is free. Now, the leaves are so far out, right? The height is like, think of logarithmic. So there's something called correlation decay that's used like in counting and sampling, that if we have a slack, even though the leaves are heavily correlated, the correlation decays for every height of the tree. So basically, the vertices incident to ET behaves as independent. Okay, that's the high-level idea. The only issue is that the slack required in, there's some calculations here, the slack required into getting this decay is E over E minus 1. So they don't get down to 1 plus little o 1 delta. Okay? But again, kind of they do a very, very smart trick. I think this often used like in Weitz, for example, algorithm for counting independence and so on. But they use a very smart idea to reduce kind of to the independent case. Okay, so we do something different. So, this is just English, right? It's not very mathematical. Embrace correlation as control. Okay? We keep the correlations but change the viewpoint. Okay, and my takeaway probably, like, it's not so, okay, it's useful for me. I learned something in this project. It's like, all right, we are interested in proving concentration about these probabilities. We had theory correlations we didn't know how to deal with. But if we can kind of look at this quantity, how it develops in time, and formulate as a martingale, you get basically very, very strong concentration, like Shannon type concentration for free. And that's what we're going to do. Okay? So remember the algorithm. So now there is actually some devil in the detail about this algorithm. So when I say probability UV both free when ET arrives, this quantity here, is it the global scaling factor over the probability of UV being free over all the randomness of algorithm, which is hard to calculate, right? It would be like, you would need to simulate the algorithm over all the random bits. I don't know how to calculate this efficiently. Or is it actually the probability that UV free is in the actual execution of that? Okay. So there's two different ways of implementing this idea. And what we will do is this executant dependent scaling. That's important. So let me explain this. All right. So when an edge ET arrives, at that point of time, some edges incident to U arrive and some edges incident to V arrive. When they arrive, they were taken with some probability PET1, PET7, PET2, and so on. Initially, these probabilities was 1 over delta plus Q, but then they're scaled up and so on. Right? So the probability we will take ET is exactly 1 over delta plus Q over the probability that it survived these incident edges. Okay? So that's easy to calculate, right? We just keep the probability that we selected the edges, and we scale up the probability we take ET with 1 over, the scale up factor caused by these edges incident to the endpoints of ET. Okay? Okay, of course, we still have this problem that we have to deal with. So let me just give an intuition why the difference between these two atoms. Okay. So when E3 arrives, what probability should we pick E3? Okay, we can only pick E3 in these two settings. Okay. One way would be to have a global scale-up factor. The probability that both the endpoints are free, you look at here the endpoints are free, here the endpoints are free. What's the total probability mass of these two scenarios? Okay, and scale up with that. That's kind of a hard quantity to compute if you are interested in algorithms, because this tree here, I only show 3 edges, but it goes up every time I get an edge, I branch twice, right? So it's like, at least naively, I would need exponential time to calculate this scale up factor. Another one is to do execution dependent scaling factor. So you can notice that in this path here, the probability that we selected E2 was 0. We already selected E1. So if I go down this path, if UV are both free with probability 1. On the other hand here, I selected E2 with a larger probability because both endpoints of E2 was free and we scaled up E2. So here, if we have an execution-dependent scaling factor, we will scale it up by 1 minus the probability that we select E2 in this. Okay, so that's much easier to keep track of, and that's what we do. Okay, so 1 over 1 minus PE2. And this turns out to be very, very important for the analysis. Okay. Is that okay? Yes. Well, exactly. Well, you see, I see it's global up to now, so we could compute it, but I only know how to compute in exponential time. So this is easier to compute, and it turns out that it's, at least from our point of view, much, much easier to analyze. I don't know how to analyze the other one. All right, so now we have to prove that this is valid, that the probabilities are valid. Okay, actually, we'll prove something much stronger, that, the probabilities that we pick an edge is like way smaller, like 10 over root delta. The reason why we prove something stronger is to bound the step size in the martingale, if you're interested. All right. Okay, so what's the idea? So we have this scaling factor, how much we scaled up ET. We can split it up to the scaling factor caused by the edges incident to U and the ones caused by the edges into V, right? So the scaling factor is just one, the product of 1 minus the probability that we select these edges. Or 1 over SU is the scale. So initially, the probability that we select all these edges is 1 over delta plus Q, right? At the start of time, you can think of if this is the next edge to arrive, we select U with 1 over delta plus Q. Okay. Now, think about when an edge F comes here incident to this. How does the probability that we select E2 change? Well, if the algorithm selects F, we cannot change E2. We cannot take E2 to E2T2, ET2. So the P new becomes 0. On the other hand, if F is not matched, we need to scale him up by 1 minus PF. You know, this happens with 1 minus PF. So PET over 1 minus PF. So this means that we are exactly preserving the expectation. Okay, the scaling factor is preserved in expectation when new edge is right. This is very important, right? So this means that we have a martingale where we look at the scaling factor at start of time. We look at when edges F arrives at the 2-hop neighborhood. In expectation, this stays the same. So you have like an unbiased random walk that goes up and down a little bit. And you want to say that it doesn't go too crazy out of its expectations. It stays with time inside this interval. Okay, and that's what we're going to do. We're going to show that along with time, this guy stays within some reasonable, fourth root of delta if you want. Okay. Okay, so if no correlations, Chernoff bound would give us Q delta to the power 3/4. Basically applying something called Friedman's inequality gives us the same. So Friedman's inequality just says if you have to bound, you have to show it's a martingale, you have to bound the absolute step size. Actually, you have to only bound the observed variance, okay, along this walk. Okay. And the plugging is this, what we get is basically we get the same concentration as Chernoff. Here we lose a log, but okay, losing here. So that's the whole actually the algorithm and the analysis. So the idea was look at this execution upon scaling factor, formulate the scaling factor as a martingale, bound the step size, the variance, apply Friedman's. Yes. So now in the remaining, yeah. Yes. Perfect. So in this matching algorithm where you're on top of stuff, in the matching algorithm, there's no requirement in delta being big. This always works. The reason that you need delta to be big is what you're saying for an edge coloring algorithm, you need it to work for all vertices and many. So you need to do a union bound, and that's like you have E minus delta, select delta to be log n. Yeah, relax. Okay. Okay, so we come on a high level. Right, okay, so summary. Okay, so what did we prove, and we will answer your question. Okay, so basically for low degree graphs, nothing interesting, but as soon as you go a little bit above log n, you can do as well as offline basically. And the key takeaway was this: if we just change point of view, use martingales, we get Chernoff types of concentration. Now, what can you do with this? And I will come to you in a couple of times. So there's natural extensions of this framework. First, there's nothing special by taking every edge with 1 over delta. You can round online any fractional matching, so you can assign different probabilities to edges as long as the probabilities are not too big. Okay, so you can basically get a lossless rounding as long as you have a fractional matching that is spread out enough. You can get the same result for list edge coloring, the generalized Kahn's result from 96, albeit you lose this little O of 1. So what is list edge coloring? When an edge arrives, you get a list of available colors for that edge. And this list is assumed to be of size at least delta, otherwise it doesn't work. So it's a generalization. You can think of the the standard problem has that every edge has the same palette. So you're allowed to have edge-dependent palettes, but they have to be of certain size. And there's another version that was introduced in 2023, is called local edge coloring, meaning that if I look at an edge E, if it's incident to very low degree vertices, I want to use colors of very low index. Okay, basically, for edge E, I am allowing myself to use colors that is maximum degree of these endpoints. This can also be done online, basically by only losing this little one. Okay, so now let me come to this that I promised the latest work. There's one slide here. So here, first of all, you cannot go to the matchings because matching you have to use randomization. Okay, so you have to work on the colors immediately. And also, one can see that actually this doesn't generalize to list coloring, it cannot do. But let me now explain why root log n, because root log n seems weird when you do union bound, right? E minus log n and E minus doesn't work. Okay. So what is the intuition? So rightly, what we did intuitive on a very high level is that every matching corresponds to every color. And what we kind of did was that every color is good with probability E minus delta. So by selecting delta to be log n, we got the nice union bound. All right. But you can observe that every color being good is a very strict criteria. I'm okay by throwing away a certain color classes, and for those edges, I just forward them to greedy, as long as the degree is small. Okay. So instead of saying the criteria that every color is good, what I say is that all colors are good, but a vanishing number of colors that is the most epsilon delta match. Now you hope that the probability that colors fail behave as independent. That's where the sweat comes. But then you get E minus delta squared concentration, and that's where the root log n. So you have two delta. You have the color palette and you have the degree. And that's it. All right, so now let me give some open problems, okay? So it looks to be a solid problem. There are some nice questions still. So in the paper from 92, they conjectured that a very simple modification to greedy should work. It's still open. So this is called randomized greedy. I have my color palette. Remember that greedy selected the lowest index in the color palette that was available. You can think of randomized greedy. Among the available colors in my palette, just select one uniform at random. Okay. They conjecture that this simple modification to greedy works. We don't know. What is interesting is, for a stronger result, this root log n we just discussed, our simulations indicate that actually this doesn't work. We don't have a formal proof, but okay. A little bit interesting to me, at least, is that this uniform at random color actually introduces biases. Our algorithm, if you look at it carefully, it will change the probabilities of selecting a color depending on the probability that this color was already used, which actually corrects for biases. So introducing these shifts actually helps you to get strong concentrations. That doesn't seem to happen if you do uniform at random. And there were some results on this argument for very dense graphs that have linear degree. The other open problem is these deterministic algorithms. So they didn't believe in deterministic algorithms at all, but now we know that such are possible. However, our proof is insanely indirect because it works as follows. Okay, so we show that we have a randomized algorithm that works against an adaptive adversary. What does this mean? An adversary that can look at how you color the graph up to now and then decides which edge to give. And that is known that if you can do a randomized argument against such a powerful adversary that can look at everything you've done up to now and then decide the next edge, that implies deterministic. But it's a very indirect way because you have to look at this giant tree of strategies of the adversary. So this doesn't lead to any efficient algorithm. It's just that there exists a deterministic strategy that works, but we have no clue how it looks like. Okay. So that is exactly. So like you have a giant tree And since there exists always, exactly. So you have a randomized item that works against any adaptive variable. So there is one of the some choice has to work against any future. Take that choice. But like that's a very indirect proof of existence. And then, of course, if you're really into the fine-grained, you could worry about the exact dependency on delta. So is it low, like we know that you need to have a delta plus root delta. In what I presented today was delta plus 3/4 delta. All right, thanks.
So since you mentioned Khan, so this list coloring or generally this type of algorithms work well also for edge hypergraph coloring, assuming the hypergraph is linear. So linear, right? So you need any two edge, so it should resemble graph, right? So the way to generalize it is to say that linear means any two edges intersecting one point. Something like that will work here.
It's a good question. So my quarter David also raised this. I think we never really went down the road. Well, I can say if you have a hypergraph where every edge has constant size, then I believe the same proof should just work. Because basically the size of the hyperedge will be the step size in the martingale. So if this is constant, it's okay. Now your intersection criteria, I don't know. Because I have to think a little. You assumed that you didn't have any bound on the size of the edges, right? You just said that the intersection should be. Right. So I have to. Yeah, you're okay. Yes. 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 Let's discuss this afterwards. Maybe I will. Okay. It's complicated. Yeah.
Okay. Any other questions or comments?
Hi, thank you for the talk. Maybe I didn't get it, but in your proof, in the main part, which part did you use your lower bound on the delta? So delta is omega log n.
You're asking where did I use that delta is the max degree? All right, so that isn't a scaling factor. Otherwise, if you get more, this only shows that, the scaling factor is bounded at the start of time when everybody's picked with 1 over delta plus q because there's the most delta edges. If you had like more than delta plus q edges incident to you, right, there's no way of rounding this. The probability space is just not big enough, right? So like, oh, I see. Where is delta's least log n? That is not shown in the matching algorithm at all. That comes in the transformation to the edge coloring. Because the edge coloring has to work for all vertices to color them correctly. So you need to apply a union bound over the number of vertices. That's where this shows up. So in other words, you could edge color your graph to be almost perfect with some errors at some points without the assumption.
Any more questions, comments? Then let us thank the speaker.